Hello and welcome to another edition of E251 PreLab Solutions. This is Professor Hiren Trada, and in today's video, we are going to look at PreLab number 4. Okay, so let's look at Lab 4 and then the PreLab questions. So Lab 4 deals with equivalent circuits and the maximum power transfer theorem. Equivalent circuits are basically the single most important concepts in electrical engineering. Basically is based on theorems that were invented in the late 1800s and the early 1900s. There was a French telegraph engineer by the name of Leon Charles Thevenin, who postulated a theory that you could represent a large linear circuit comprising of linear elements with just a single voltage source and a single resistor in series. That voltage source is known as the Thevenin voltage. The resistance is known as the Thevenin resistance. And that circuit is known as the Thevenin equivalent circuit. A few decades later, a Bell Labs engineer by the name of Edward Norton was working with audio sources, and he postulated his own theory stating that you could take the same large linear circuit and represent it with a current source in parallel with the resistance. And that theorem and the theory was named after him, came to be known as Norton's theorem. Circuit came to be known as the Norton equivalent circuit, which are shown in figures 1b and 1c. Okay, figures 4-1b and 4-1c. Okay, so let's take a look at the PreLab questions. In this PreLab, we have we have 6 questions. The first one asks you to determine the voltage and current for the circuit shown below. Okay, this is just to get you started and prepared at calculating the voltage at any output terminals. So let's take a look at how we are going to solve this. And let's switch over. All right. So PreLab 4, as I was mentioning, has 6 questions. The first one right here, you're asked to calculate the voltage V at the output on the right. Okay. So now what I've done is I've just drawn the schematic a little bit differently on the right. All right. So let's just post this here. And you can see R1 and R2 are connected in series. We are taking the output across the 560 ohm resistor, which is right here. So V is calculated directly across the 560 ohm resistor. Okay. Now, even though we're taking the output here, we are not connecting anything else. This is just a tap, meaning you're just tapping into the circuit to measure the voltage. When you measure the voltage, the voltmeter has infinite resistance, meaning it's not going to affect the circuit or alter the circuit in any way. So you can consider R1 and R2 to be in series. Okay. And if they are in series, you can apply Ohm's law and determine the total current I that is flowing in that circuit. Okay. Once you find I, the same I is going through R1 and it's also going through R2. You apply Ohm's law again. Oh, actually here, the circuit. You apply Ohm's law again and you calculate the voltage across that resistor, R2. All right, 2-step answer. So R1 and R2 are in series. You apply Ohm's law, you determine the current I and then the voltage V. All right. Now, we are told to place a short between the terminals A and B. What does that do? Well, when you place a short across any component, that component is effectively removed from the circuit. So if you think about it, when I comes through R1, if this short has 0 ohm resistance, right? Doesn't matter what value R2 has, even if it's just 1 ohm, all of the current is going to go down this short path. So R2 is effectively removed from the circuit. It may as well not be part of the circuit at all. So now you have one voltage source, you have one resistor, you again apply Ohm's law, and you calculate the current I. And that's it. That is problem one. Now, question number two. Question number two asks you to find the Thevenin resistance as seen by the load at terminals A and B. Okay, we have three circuits in here, A, B, and C. Right, circuits A, B, and C. So to find the Thevenin resistance, all we need to do is find Req between the two terminals. And the way we do that is we reduce all independent sources to zero. Replacing or reducing a voltage source to zero means you replace the voltage source with a short circuit and you replace the current source with an open circuit. All right. And the way that works is because if you have a voltage source and you want to reduce the value of the source between A and B to zero, the only way you can have the voltage equal to zero is if both the terminals are exactly the same potential. And the only way we can do that is to place a short in there. So we have a short circuit between A and B. All right. Current source, same principle. If you have a current source in a circuit and you want to reduce the value of that source or current to zero, well, the only way to make sure that no current flows through a point is if there is a break in the connection. And so we replace it with an open circuit. All right. So we take our circuits. Wherever you see a voltage source, you replace it with a short. Wherever you see a current source, you replace it with an open. Current source, I mean, replacing it with an open simply means you remove it from the circuit. That's all it means. Okay. That's all it means. So then you rearrange or redraw the circuit diagrams to reflect the change in the sources. And then you simply calculate Req at the output terminals A and B. Right? You simply calculate Req for each of these three circuits. Now, when you calculate Req, the best thing to do, if you want to calculate Req between a certain pair of terminals, always best to start at the farthest end and then move towards the terminals, reducing it step by step. Okay, so in this case, Req, if I start at the farthest end I have R7, R8, and R9 in series. And so I would have R7 plus R8 plus R9. And that series combination would be in parallel with R5, which would be in series with R4 and R6, which would be in parallel with R2, which would be in series with R1 and R3. And that is my total Req. And my Thevenin resistance, RTH, is equal to Req between those two terminals. All right, that's how you would find Req. Now, oftentimes you might be faced with circuits where you cannot actually reduce, or it's not quite easy to reduce it just by combining it in series and parallel. Well, then I would like to show you a technique where you can do that. So if you have a circuit like this and you have output terminals, in this technique, what you would do is you would draw out the measurement terminals some distance away from each other. The goal is to draw all the resistors vertically going from A to B. okay, going from A to B. So if I start at terminal A, I have resistors R2 and R3 connected, right? Now, my goal is to get to point B starting from A. So if I start from A and I go from R3, I can see that R3 is connected directly to B. So I would draw out R3 and R3 goes directly to B. So I'll extend a line right there, right? Then let's tackle R2. Well, R2, I'm going to draw it some distance away. Is right here, connected to A, right? This node. The other end of R2 is connected to R1, and the other end of R1 is connected to R4, which goes to terminal B. So if I was to draw this out vertically, I could draw it as R1, R4 going all the way to B. So R1 and R4. And there is one more resistor, right? There is one more resistor, R1 and R4. And that resistor is R5. If I take a look at R5, R5 is actually connected at the junction point of R1 and R2, meaning right here, and it goes all the way to B. So when I draw R5, I'm going to draw it like this. And now I can quite clearly see that R1 and R4 are in series, which are then in parallel with R5, which is then in series with R2, and this entire branch is in parallel with R3. Okay, so this technique pretty much works with any circuit. You simply have to take it step by step. And again, you might have to redraw the circuit 3 or 4 times, but eventually you would get the answer. Now, again, this technique does not guarantee you that you will get one single resistance, because all circuits are not reducible. But the goal is to actually draw all the resistors vertically, and so at least it would make a bit more sense. Okay, so that was question number 2. Let's go to question number 3. Oh, sorry, I think I just realized that I was not showing or not sharing the screen here. So let's see, I might have to do all of that all over again. All right, let's do this. Okay, so problem number 2. Problem number 2, to find REQ, we reduce independent sources to 0. When you reduce independent sources to 0 means replace the voltage source with a short circuit, replace the current source with the open circuit, and then determine REQ between the open terminals. To find REQ at any terminals, I would always recommend start at the farthest end and move towards the terminals. Okay, and so in this case, when we do that, we start at the farthest end. We get R7 plus R8 plus R9. They are in series, and that series combination is in parallel with R5. That parallel combination is in series with R4 and R6, right, which is here. And that would be in parallel with R2. So parallel with R2. And then finally, that would be in series with R1 and R3, right there. So that's REQ for that example. Now, RTH, Thevenin resistance, is always the equivalent resistance measured between those pair of terminals. But there are some circuits that might have a weirdly drawn schematic. So to analyze those circuits, I would recommend using this technique. So in this technique, what we're going to do is We are going to draw out the terminals of analysis, meaning A and B, spaced far apart. And the goal is to actually connect all the resistors vertically going from A to B, right? So if I start at A, I can see I have two resistors at A, R2 and R3. Now R2 goes all the way around here, goes all the way to B. R3 actually just goes and connects directly to B. So I'm going to draw out R3 first, right? R3 starts from A, goes all the way to B. Then draw out R2. R2 is connected to R1. R1 is connected to R4, and R4 is connected to B. That's it, 4 resistors done. Then I have one more resistor, and that resistor is R5. I can see R5 is connected up top here between the points of R2 and R1. And it starts from there and is connected all the way to B. So I'm going to draw the line and connect it right there. And that shows me that R1 and R4 are in series, which are then in parallel with R5, which would then be in series with R2. And this entire branch is in parallel with R3. Okay. So this technique works for almost any circuit. As long as the circuit is reducible, you would be able to arrange all the resistors vertically and reduce them in series and parallel. Okay, so that's basically question number 2. Now, question number 3 asks you to find the Thevenin equivalent circuit at terminals A and B as seen by the load. Okay, as seen by the load. Now, when you find VTH and RTH as seen by the load, the first thing you should do is remove the load from your analysis. Okay, you have to remove the load from your analysis. So no matter which circuit you're doing, whether you're doing RTH, whether you're trying to find VTH, whether you're trying to find IN, you have to remove that load component from your analysis if it says as seen by. Okay, so for RTH, I draw out my circuit, and the circuit looks like this with RL removed and REQ at the terminals A and B. Now, you already know what you need to do. You have to reduce the independent sources to 0, meaning replace the voltage source with a short circuit and a current source with an open circuit. You only have a voltage source in there, so replace it with a short, calculate REQ between A and B, and you'll have your answer. Right? That's your RTH. To find Thevenin voltage, well, you go back to the original circuit. Original circuit is like this. There should not be RL, right? RL should not be there. And simply calculate the voltage at those terminals A and B. Now for this circuit, you can choose node voltage analysis, mesh current analysis, or series parallel equivalent analysis, meaning you reduce the circuit to one single resistance and apply Ohm's law and find the voltage and currents that way. But I can see that there's one voltage source and only 3 nodes in the circuit. And so it makes sense to use node voltage analysis. If I use node voltage analysis, all right, hold on. The system has crashed. Let's see. All right, let's see here. I share screen again. Okay. So as I was saying, you can use node voltage analysis. In node voltage analysis, we pick a reference node first. So if I choose the bottom node as my reference, which is node B, if BB would be 0 volts because B is my reference. Let me call this node on the left as C and the node in the middle as D. Okay. So if VB is 0, if VB is 0, VC is equal to VS for the purposes of this analysis, right? Apply KCL. Assume branch currents IR1, IR3, and IR4. IR1, IR3, and IR4. Assume branch currents, apply KCL at node D. And then apply Ohm's law and express each resistor voltage in terms of the node voltages. There are only 4 nodes in the circuit, V, A, B, C, D. VB is 0, VC is equal to VS. You write an expression for VD and you simply be able to solve it directly. Once you find the voltage at VA, that would be your VOC because the reference node is B and VOC is measured with reference to B. So VOC is simply equal to, well, voltage at A with reference to B. So VAB. All right. That might seem like a lot, but when you sit down to solve this, it is rather straightforward. So again, if you get stuck anywhere, please reach out to me or reach out to your other professors. Now, let's go to question number 4. Question number 4 asks us to find the Norton equivalent circuit for problem 3. Now it's the same circuit, and so the circuit for finding finding Norton, you have to go back to the original circuit. And once you go back to the original circuit, we place a short between the terminals A and B. And the short circuit current, ISC, would be the Norton current for that circuit. Okay. One word of caution. Each of these 3 quantities is independent of each other. RTH, IN, and VTH have no bearing on each other whatsoever. When you're trying to determine the quantities in any one of these circuits, you forget about the previous analysis, you forget about the previous circuit, because each circuit is independent of the other. All right. So you analyze the circuit. You can analyze it again using node voltage analysis, mesh current analysis, or you could use series parallel equivalent analysis again. Doesn't matter what you choose. I would recommend using mesh current analysis, because if you choose mesh current, let's see, there are 3 meshes, and apply KVL. So there are 3 meshes, there are 3 unknown variables. But if I was to label this as, let's see, I1, I2, and I3 as my 3 meshes, I can say that I2 is equal to ISC because they're in the same direction. So if I find I2, that is my Norton current. Okay. You can of course use node voltage analysis, find the voltage at between the 2 nodes, and then find current that way. Doesn't really matter how you do it. Okay. You can find the currents through the resistors and apply KCL at node A, right? Voltage VS would send the current this way. The current would go through here, and it could either go through here or it could come back in here. But that remains to be seen depending on our analysis. So I would try to avoid using that method. I would say simply choose either node voltage or mesh current and just solve it that way. That would be a little bit easier than using any other method. Then you're asked to verify your solution by simply applying Ohm's law, right? Divide the Thevenin voltage with the Norton current and see if your answer matches up with RTH that you calculated earlier. Okay, that's a verification of your analysis. Now, question 6 or problem number 6 deals with maximum power transfer theorem. Now, maximum power transfer theorem simply states that in order for maximum power to be transferred from a source circuit to a load circuit, the Thevenin resistance of the circuit should equal the load resistance, meaning RL should equal RTH. Okay, that is the criteria. RL should equal RTH. So maximum power transfer occurs when the load resistance is exactly equal to the Thevenin resistance. So in this question, 6A, you're being asked to find the value of RL that will provide a maximum power transfer to the load. So understanding the question is the most important part, right? What value would provide the maximum power transfer? Well, when RL is equal to RTH of the circuit. And so all you need to do is you need to find the Thevenin resistance of this circuit as seen by the load resistor RL. Okay, load resistor RL. And that means you need to remove RL from your analysis. Remove RL from your analysis and find REQ between the terminals A and B. Okay. Of course, you have to reduce the voltage sources to 0, meaning replace the voltage source with a short circuit. So you redraw that circuit, find REQ between those terminals, and that would be your value of RL. All right. Now, second question, 6B asks you to calculate the power in watts delivered to the load RL for the value of RL that you determine in part A, which is right here. Okay. So again, you have the value of the resistance RL that you determined in part A. All you need to do is now find PRL. Well, PRL, if you remember from chapter 1, power is the product of voltage and current. Power combined with Ohm's law can also be written as V square over R, or you can write it as I square times R. So what you can do is you can find the current going through RL, or you can find the voltage across RL. A voltage across RL, sorry, the current through RL would be the Norton current. So you'd have to perform a Norton analysis. The voltage would be the Thevenin voltage. Either case, you have to do either a Thevenin analysis or a Norton analysis to determine either the Thevenin voltage or the Norton current as seen by RL. I would say Thevenin voltage would be the easier of the two. Well, actually, no, Norton current would be the easier of the two. Either case, it does not actually matter. It's a one-step answer. If you want to find the Thevenin voltage, you can choose voltage division. If you want to find Norton current, it would simply be a Ohm's law. Okay, so I would say both of them are rather straightforward and simple. Norton current would be slightly simpler than the voltage. Once you have the voltage or the current, you can find the power for the load resistor by any one of these two equations. And that's, well, that's 6B. For 6C, we are saying that RL is 10 ohms. If RL is 10 ohms, we need to put a resistor R4 in parallel with R2 to provide maximum power transfer to the 10 ohm load resistance. So then what is the value of that resistor R4? Well, it's just an extension of A and B. So what you need to do is this. RL is 10 ohms. If you want maximum power transfer, then the RTH value for the circuit should also be 10 ohms. Okay, RL should be equal to RTH, right? So the new REQ or the new RTH has to be 10 ohms. All you have to do is use this, right? The new REQ, which is 10 ohms, will have the old REQ from part A in parallel with R4. You equate the two and calculate or solve for R4. And that's it. That's 6C. All right, that's 6C. So as always, hope this was useful. If you have further questions, feel free to reach out to me. My email address is htrada@calpoly.edu. Reach out to your professors, 251 or 201. And we'd be more than happy to help you out. All right. Good luck with PreLab number 4.